All right. Welcome back to Calculus 1. This will be the 9th lecture of the course. And in this lecture, we're going to discuss yet another differentiation rule, and a powerful one at that. So in the previous sections, we've talked about a lot of the sort of standalone differentiation rules. And in the most recent lecture, prior to this one, lecture 8, we talked about the product and quotient rules, which are very powerful. Take two functions that you can differentiate, the product of those functions we can now differentiate, and the quotient. So this rule, the chain rule, is similar to those, but here we're going to be discussing how to differentiate composite functions. Okay, so let's call this section 2.4. And let's call it the chain rule. Okay, so the chain rule, as I just said, is going to be a rule that applies to composition of functions, so composite functions. Okay, so let's talk about what this rule is going to enable us to do. So we'll have like a without section over here, and a with chain rule section over here. Okay, just to get a sense for this. So without the chain rule, we're fine differentiating y equals x squared plus 1. With the chain rule, we'll be able to differentiate y equals the square root of x squared plus 1. So this would be a composite function. So this is a function kind of inside of another function. Over here, we can do things like y equals sine x, no problem. But what about y equals sine 6x? All right, so here you've got something like a composition as well. Y equals 3x plus 2, or just any polynomial. Well, now we can take polynomials or other functions raised to a power with the chain rule. And then we've discussed y equals e to the x, but what happens with functions like y equals e to the 2x plus 1 power? All right, so these over here are all examples of the types of things that the chain rule is going to enable us to differentiate. All right, so let's talk about the theorem itself, the chain rule theorem. Okay, so what does this thing say? Let me double check that this is focused really quickly. Okay, looks better. Okay, so the statement here is going to be a little mucky, but don't worry. Let's just push through it, and then once we have the theorem out, we'll prove it, we'll talk through it, we'll do tons of examples, so it'll be quite clear by the end here. So if y equals f of u, okay, is a differentiable function of u, okay, so y equals f of u is a differentiable function of u, and u equals g of x is a differentiable function of x, okay, then, now here's where we kind of compose everything, f of g of x is a differentiable function of x. Okay, and the way we would kind of write down what that derivative looks like, it would be, there's a couple ways to look at it. We'll look at it first this way, dy dx, it's going to be equal to dy du times du dx. Okay, so the derivative of y with respect to x is equal to the product here of the derivative of y with respect to u and the derivative of u with respect to x. Now, a better way, this notation is fine in some instances, and I think in the examples we'll kind of flip between this and the following, but I think one way that's possibly more intuitive would be to say, and this is equivalent, that d dx of f of g of x is equal to f prime of g of x times g prime of x. Okay, so these are equivalent statements. Obviously it says equivalent there, but just these mean the same thing, but obviously the notation is very different. Okay, so the notation is very different here. And I think in a lot of cases this is more intuitive, but we will see where this is useful as well. Like, they're both useful, but I think generally people tend to gravitate towards this over here. Okay, so basically the idea is, and I think, again, let's just focus on this side here for now. The idea here is that if I have a function f of g of x, now we've seen composite functions like this, okay, f of g of x, and I want to take the derivative of that. So this is f, where you can think of a function g as being sort of built into the interior of the function f. So this is a composition of functions. If you want to take the derivative of that, then what this is basically saying is that you want to take the derivative of kind of the outside function, leaving the interior part of the function alone, and then you want to differentiate the interior part separately, and then the product of those two is the derivative of the overall function. Okay, so I know that's a mouthful, right? But we'll see some examples. We'll break this down a little further just to make sure that you know, intuitively people are following this. But before we do that, let's just prove the statement. It's very simple to prove, given things that we've seen already, kind of given some of the definitions that we've used in the past. So let's go ahead and just prove this quickly. Let's let h of x equal f of g of x. So this is our composition here. All right, we're just going to call f of g of x, we're going to call it h of x, right, for convenience. Now, what we're going to do with this, for this proof, is we're going to recall a definition of the derivative that we introduced in a prior lecture. I believe if you go back and you look at the lecture entitled Intro to Derivatives, we introduced this this definition. We said there that the f prime of c, the derivative of f at the value of c, is equal to the limit as x approaches c of f of x minus f of c over x minus c. Okay, so that was the limit that we used to as an alternative definition of the derivative. Okay, so I'll leave it to you to go back to that lecture and look that up. But we're going to use this definition because when we use this definition, this proof is very, very simple and straightforward. So let's basically encode our functions into this definition here. So h prime of x is equal to the limit as x approaches c. Now f of x here, well, we're talking really about h of x, which is f of g of x. So what I'm going to write here is f of g of x, okay, minus f of g of c divided by x minus c. Okay, so simple substitution here into the definition of the derivative. And we're going to use a, classic proof technique here of multiplying the top and bottom by the same thing to introduce some new terms into the expression. So we'll start with these things again here, like so. Now what we're going to do is we're going to multiply the top and bottom by g of x minus g of c, right? So obviously we can do that without changing the way, the value of the expression, right? Multiply top and bottom by the same thing. And then we're just going to do a little rearrangement here. So just a little rearrangement thing. And so I think we'll leave this here and then bring this and swap the places of the denominators here. So when we do that, we get over here we've got g of x minus g of c, all divided by x minus c. So you see what we've done is we've just kind of swapped those. Okay. Now what we need to do, well, the limit of this product, right? So we know that we can take that limit and we can kind of evaluate these two pieces of the product separately. And so when we do that, we get this guy here. So we get that piece there. Times the limit as x approaches c of this guy. Okay, now let's just bracket these off so that we know that these are totally separate now. All right. Now, what is this one? Okay, well, first of all, like, what is this one? This one is straightforward, right? This is the definition of the limit of g prime of c. So this is g prime of c. This is the definition of the derivative g prime c, right? That's what I meant to say. So you've got g prime of c over here. And now what's happening here? Okay. So it's important to notice here that the denominator, so this term here, for example, is the argument here. And this term here is the argument here. Okay. So what you can do is you can kind of look back up here, and I'll notice here that this is the argument here, and this is the argument there. We have the same setup down here. We've got the arguments. You're dividing f evaluated the two arguments by the two arguments, right? So this here is basically f prime of g of c, isn't it? All right, hopefully you can see that, right? If you look back here, if this is f prime of c, then this is f prime of g of c. Okay, just take that same structure and plug in g of x and g of c respectively. Okay, so basically that's it then. We've shown that that algebraically everything just kind of falls out of this definition. Okay, and so that is the proof of the chain rule. Now, obviously, that wasn't the most helpful proof in the world, but I think it's kind of instructive sometimes to look at proofs, even if they're not tremendously helpful, just because it's good experience. It also is like, oh, I mean, I can see how, you know, using this definition and then just basic algebraic techniques, I can in fact derive the result, right? And it doesn't always have to be the most complicated and involved proof in the world. You know, frequently, if you're, you know, tracking on principles that you've already, you know, established, you can very frequently just combine already established results in simple ways to prove powerful theorems. So that's kind of the example here of the chain rule. All right, now let's talk more about this and do some examples and make sure that it's clear what we're exactly up to. Okay. So when we use the chain rule, I would say it's important / helpful to think of the composite function as having an inner and an outer part, right? So if your function looks like this, right, then you can kind of think of the g of x as the inner part, right? And then the f of whatever as the outer part. Okay, and so this inner part, outer part, this is kind of what drives the chain rule, right? You have to be able to identify these two parts of a composite function in order to even apply the chain rule. So let's do an example here where our focus will be not on calculating a derivative, but just identifying the two parts of the derivative. So let's do a couple of examples, actually. Let's start with this one, y equals 1 over x plus 1. Okay. So we want to find the inner and the outer parts of this function. So the outer part, you can write as this, right? So the outer part, you could write it as like y equals 1 over u. Okay, so that's like the structure of the outer piece of this function. And then the inner part would be u equals x plus 1. Okay? Right? And then you can see, of course, that if I say y equals 1 over u, if I evaluate that, if I plug in what u is, then I get 1 over x plus 1, right? The u is x plus 1, right? So you can see how these two pieces can be, combined. You can use the one inside of the other to form the original function. Okay, let's do another example. What about y equals sine of 2x? Okay, so here you would be able to say, well, let's let the outer part be y equals sine of u, and let's let the inner part be u equals 2x. Okay, so obviously if I take this and I plug it in for u, y equals sine of u, which equals sine of 2x, right? So that's easy to see, kind of pulling them apart here. And this notation is useful to get into using, especially if you're going to use the first version of the chain rule that we saw, the one that involves, let's see, which one is it? Yeah, right here. So if we're going to use this notation in particular, then it's helpful to start writing things in terms of y is a function of u and u is a function of x. Okay. So that's that. That's a good example. Let's do one more like this. This is a common example, something like this, like a polynomial 3x squared plus 1 inside of a root. Okay, so the outer function would be y equals the square root of u, right? And u equals 3x squared plus 1. Okay, then these would combine. Y equals the square root of u, which is equal to the square root of 3x squared plus 1. So it combines like that. Okay. All right. Very good. So these are just 3 examples where you've got the outer part, the outer part, and the outer part. And you've got the inner part, right? The inner part and the inner part, right? And then in each of those examples, the two can be combined to form the original function. Okay. Now let's go ahead and actually use the chain rule and find some derivatives and see how this works. Let's start with this example. Let's say y is equal to x squared plus 1, and then let's cube that whole thing. All right, so remember the chain rule then says that dy dx is equal to dy du times du dx. Okay, so first we need to know what the y function is, and then the outer function and the inner function. So you can kind of think of as this is the outer function, and this guy here is the inner function. Okay, so you need to establish those things. So you can just kind of come off to the side and say, okay, well, this is equal to, the outer function is y equals u to the 3rd power, and the inner function is equal to x squared plus 1. Okay, so you kind of pull it apart into the 2 pieces, right? And then you just make sure that when you put those together again, you do indeed get the original function. Just make sure you've not omitted any piece of it. And yep, so those work. So then you can just come down here and plug these into basically the notation. It kind of does it for you. So dy over du times du over dx. I'm rewriting this. You don't have to necessarily rewrite it. And so instead of y, we're going to plug in d du of u cubed. Okay, and then instead of u here, we're going to plug in what u is. So this would be d dx of x squared plus 1. Okay, and we can easily calculate these derivatives. We've done this a bunch of times already, right? So this would be 3u squared right here for this piece. And then this piece here is what? 2x, right? Okay. All right, good. So we've got the form of the derivative. Now the last thing to do, of course, is you don't want to leave things with the u in there, right? You need to plug everything back into x. And so that would mean you have 3 times x squared plus 1, right? And then you want to square u, so that would be squared times 2x. All right, and then of course you could clean this up a bit. Maybe you could say 6x times x squared plus 1 squared. That would be the best way to write it. So there you go. So that's an example of using the chain rule to actually calculate a derivative. Okay, let's try another example. Examples are the way to go here. Once you do one, you should probably just do another one. All right, let's say our derivative, or our original function, is 3x squared plus 1. And this time we're going to take the square root of that. Well, our outer function would be y equals the square root of u, which you might want to write as u equals u to the 1/2 power. And then our inner function is, of course, the 3x squared plus 1. Okay. So then dy dx, we know that that's equal to dy du times du dx. Okay, and we can plug everything in. Of course, I'm again being very literal here. Plugging in y, we get u to the 1/2 power, and then plugging in u, we get 3x squared plus 1. All right, so now everything is in place, and all we got to do is crank out the derivatives. And when we do that, u to the 1/2 becomes what? So it would be like 1/2 u to the negative 1/2, wouldn't it? Right, that's the power rule that we learned. And then this one here is a simple polynomial, so this would be 6x. Okay, so let's clean this up. We don't really like having those negative exponents. So this would be the same thing as 1 divided by 2 times the square root of u times 6x. Right, so just bringing the u to the bottom, and then recognizing that u to the 1/2 power is the square root of u. Okay, and then the last step, right? We don't want that u in there, so let's plug this guy in here. So 1 divided by 2, and then it's 3x squared plus 1, and that's the square root there. And then really it's times 6x, so let's just put the 6x up here. There we go. And I guess we could simplify a little bit and have 3x over 3x squared plus 1 square root. There we go. So this would be the derivative of that guy. All right. No problem. No problem, hopefully. Hopefully. Let's take a look at another example. This is a good one. Let's look at y equals 1 over x plus 1. So we kind of talked about this one. We did the inside-outside piece. So outside function is y equals 1 over u. Inside function is u equals x plus 1. Okay, so recognize the structure here, and that when you combine these two, you would get the original function. So then the derivative, dy dx, is equal to dy du times du dx. Now, something I didn't mention, but you probably noticed that, I mean, the chain rule is obviously true. The du's would cancel here in the notation, which is why this notation is nice. You can see that cancellation there, and you're left with dy dx equals dy dx, which is obviously true. So this is a nice notation to see that. Plugging in for y, we have 1 over u. And then plugging in for u, we have x plus 1. Okay, so how do we differentiate these two? So the 1 over u, right? What's the 1 over u become? Well, you might want to do one more step just to have this in a nice clean form, especially if you're kind of beginner, right? It's sometimes easier if you have it in a very explicit form. So just bring the u to the top and convert the exponent to -1, and then it's really obvious what you have to do to differentiate this, right? You would say this is equal to -1 u to the -2 power, this piece here. And then the other one, of course, the x plus 1, well, that's just 1, right? The constant is 0, the x becomes just 1, and so it looks like this. So let's clean that up a little bit. So that's -1 over u squared, right? And the u we see here is x plus 1, so we can plug that in. -1 over x plus 1 quantity squared, like that. All right, so that's another example of using the chain rule. Again, this notation is nice. A lot of times when you get a little more used to the chain rule, you might switch over to the other notation. Certainly the other notation is easier to talk about, I think, but well, that's a matter of opinion. That's totally a matter of opinion. Let's talk next about like kind of a special case of the chain rule that is very frequently used. So a special case of the chain rule, which a lot of books will sort of give, like allocate a theorem just to this special case. So a special case of the chain rule is called the general power rule. We already talked about the power rule, right? The power rule said, hey, look, if I have x to the n, right, then d dx of x to the n is equal to nx to the n minus 1. Okay, so that's the power rule that we talked about already. There's a more general case of it, right? So when you have a function such as y equals x squared plus 1 to the third power, this doesn't exactly fit. I mean, this is not the exact same form, right? So the general case of the power rule is really, I mean, you can see how this would be just the chain rule, right? Where you could say y equals u cubed, u equals whatever's inside there, in this case x cubed plus 1. We could easily differentiate this to get dy dx equals d du of u cubed times d dx of x cubed minus or plus 1. Right, then you would see that this is 3u squared times 2x, or 3x squared. Right? And then you could see that this would be the u, of course, you would plug back in the x cubed plus 1, and then you still have the 3x squared outside here, right? Oh, and sorry, this should be squared there. Yeah. So this is an example of the general power rule, the kind of formula that you could use the general power rule on. So let's take a look at this. We'll write the theorem down here, and then we'll talk about it a little bit. So if y equals u to the x raised to the nth power, where u is a differentiable function of x and n is a rational number, so I guess I'll write that where u is differentiable in x and n is a rational number. Okay. Then the form of the derivative is very predictable here. So it's d dx of u to the n. Right? It's just going to be, here's the power rule part of it, n u to the n minus 1. Now, but remember, u is itself a function, so the chain rule has to come into play, times u prime. Right, so the front piece of this is just using the power rule, times u prime makes it the chain rule, makes it more general. So the example here is that the variable isn't just u, there's some larger function as taking the place of u here. Okay. So this approach is, you know, like a literal application of the chain rule. But many find that it's a useful shortcut for functions like this. So it's very common. Okay. Now, one thing I want to note here is that in the case of like the basic y equals x to the 5th power, for example, like that, what we just talked about really does work here, right? Because the dy dx here would be, you know, so this has got that form of u to the x, where u to the x is just x, and raised to the nth power, where n is 5. So you can use the general power rule on this, and what you'd end up doing is you'd say, oh, this is 5x to the 4th power times the derivative of the inner piece, which is just, in this case, x, so times 1, right? So you see that this form really applies to all of the things that the power rule initially applied to, but now it's more general in that this function here doesn't have to just be a single x, right? It can be, you know, a polynomial, it could be a trig function, it could be whatever, right? But you see how this rule that we just learned, we've really been doing the chain rule implicitly all this time, but it's just that this was kind of a special case where the derivative of the inside function was always equal to 1. Okay, so hopefully that's clear. Let's do some examples here. So let's take a look at this one. This is a little more complicated example. So we'll say y equals 3x minus 1 divided by x squared plus 3, and then the whole thing is squared. So we're going to use the chain rule here, okay, but we're going to have to be a little bit careful, okay, because this is a kind of a more complicated function. Let's first talk about what the inside and outside functions are. So you've got y equals u squared, okay, so just think of this whole thing as the u, and then you've got u equals 3x minus 1 divided by x squared plus 3. Okay. So let's set this up using the chain rule. We won't take any of the derivatives yet. We'll just set it up for now. So then dy dx, and just to refresh our memories, is going to be equal to dy over du times du over dx. Okay, now y in this case is just u squared, so this would be d du of u squared. And then u is this complicated thing here, so it would be d dx of u, 3x minus 1 over x squared plus 3, right? So that guy. Now, this derivative is straightforward, right? Super easy, power rule, no problem. What about this one? What do we have to do over here? Well, this is a quotient. It's a ratio of two polynomials, right? So we're going to have to use the quotient rule probably on this. That would be the sort of the most straightforward way to do it. So here's an example where we're using the quotient rule inside of the chain rule. Okay, so let's sort that all out. So I'm going to leave everything as is. I'm not going to differentiate anything yet, just because I want the ultimate form of the derivative to be really clear. Now this derivative here, remember, this is going to leverage the quotient rule, so it's low times the derivative of the high, so it'd be x squared plus 3 times d dx of the high function, which is 3x minus 1, minus the high function, 3x minus 1, times the derivative of the low function, x squared plus 3. And then the whole thing is divided by the square of the denominator, so x squared plus 3. We'll square that whole thing, like so. Okay. So this seems like a pretty involved derivative, but notice all of these little components are real easy to differentiate. That's super easy. That one's also easy. This one couldn't be easier. Like, the hard part about this derivative is not the actual differentiation, it's the setup, and like sort of keeping track of the fact that you're using the chain rule first, and then inside the chain rule you have to use the quotient rule. So kind of setting up those bigger derivative rules. Okay, and it's not uncommon to see this type of thing, and it's not uncommon to see this type of thing, and also the product rule, perhaps. Okay, so so just get, my best recommendation would be get in the habit of just writing it out. Too many times, if I see students who are just kind of like, they think it's worth like kind of skipping over this step to try to just do it right away. I don't know if it's like they physically don't want to write more. Or if they actually think that the writing part isn't helpful. But the writing part is very helpful. This is the hard part of the problem, is the setup. And if you try to skip over this just to save having to write an extra line, it's not a good habit to get into. You're just going to want to write it out. You're much less likely to screw it up if you just write it out. Because once you've got it written out, it's straightforward, right? We can calculate all these derivatives. So this is what, 2u? And what do we got here? So the x squared plus 3 stays the same. What's this derivative? It's just 3. And then you've got over here the 3x minus 1 stays there. And this part here, what's that derivative? 2x. Right, and then the whole thing is divided by x squared plus 3 squared. Right, and you can do a lot of cleanup here. But maybe what I'll do is just plug the u back in first, right? So the first, well, now let's clean this up first. So you've got 2u, and then you've got, let's see, so this would be 3x squared plus 9 minus 6x squared plus 2x, I believe. Okay, and then down here it's x squared plus 3 squared. So we could probably clean that up just a little more, just to be sure. So 3x squared minus 6x squared, negative 3x squared, and then plus 2x plus 9 over x squared plus 3 squared, right? So, okay, now let's plug in the u, right? So remember, this is 2 times, now up above here you can see what u was, 3x minus 1 divided by x squared plus 3. So let's plug that into the expression. You don't want to drop that. So 3x minus 1 over x squared plus 3. Right, that's the u, and then this whole part is still in here. Okay, so that's good. And I mean, some of the stuff we can combine additionally. I'm going to just combine the denominators in the name of kind of doing like brevity here a little bit. Well, maybe I'll combine these two. So you've got 6x minus 2, and then that's going to be times this whole thing, negative 3x squared plus 2x plus 9. And then the denominators, note they're the same, so I can just increment the exponent. So x squared plus 3 to the 3rd power. Okay, and so that would be, that's a good, I mean, you could, obviously you could distribute here, kind of combine these, expand this, and, you could probably get a different form that's possibly cleaner, but this is good enough for now. All right, so notice this was, this function is where we started. We used the chain rule, found the inside-outside pieces, used the chain rule to set it up initially, right? So the derivative of the outside times the derivative of the inside. We notice that the outside is an easy function to differentiate. The inside, however, requires the quotient rule. So we set all that up, got it all set up, and then finally calculate, all the derivatives, and then it's all just like algebra simplification. Okay, so that's a great example. Great example of the chain rule in action. Here's a simpler one. Let's try another one, just kind of a different flavor. Let's say y equals sine of 2x. Can we differentiate this? Well, not without the chain rule we can't, but with the chain rule, super easy. This is y equals sine of u, and u equals 2x. Right, so dy dx equals dy du times du dx. So that's d du of sine of u, and times d dx of 2x. And, well, the derivative of the sine, if you recall, is the cosine. So this is cosine of u, right, times, what's the derivative of 2x? Just 2. Right, so you've got 2 cos of u, which is just 2x. Okay, so that's very doable, right? Very simple, right? If you just recognize, oh, this is a composite function, I know the two parts, I can easily differentiate using the existing rules that I know. Then I just have to apply the chain rule and kind of structure it properly. How about this example? Let's let f of x equal e, and then to the 2x plus 1. And then from that, we're going to subtract cosine of 2x minus 1. Okay, so we've got kind of two functions subtracted. There's a difference between two functions, so we'll have to use the fact that we can differentiate both of them separately will come into play here. Both of these are composite functions, so the chain rule is also going to be used. All right, so we'll use the chain rule twice. So let's just look at this first and just evaluate what our inside-outside functions here need to be. So for this one, your outside function is y equals e to the u power. We can easily differentiate that. And then our u function is 2x plus 1, right? So that one's straightforward. So that's this piece. Let's do the same thing over here just to make sure we can see what's going on. So over here you've got y equals cos of u, right? And u equals 2x minus 1. So notice when you plug those together, you get the original function. Right, so what we're going to do is we're just going to use the structure that we've established here together with the fact that the derivative of the overall function is just the derivative of the two parts subtracted. Right. Okay, so f prime of x is going to be equal to, well, it's going to be du of this guy, so it's dy du, and the y is e to the u, times d dx of this guy. All right, so we'll plug that in. Okay, and then minus, and then we have to do the chain rule over here, but on this structure, so it'll be d du of cosine of u times d dx of the u function, which is 2x minus 1. All right, not a problem. All of these are functions we've seen before. They're all straightforward. So e to the u is just e to the u. The derivative is e to the u. This guy here, the derivative is just 2. Nice. The cosine, what's the derivative of the cosine? Well, it's negative sign. That one's slightly hard to remember that the negative is on there, but just have to kind of remember it however you remember it. And then this one over here, the derivative is 2. Okay, so the structure altogether is 2e to the u plus 2 sine of u. Now, some care needs to be taken here because you've got u and which u are you talking about. So maybe it's a good idea to label these as u1, u2. You can do that if you want to. Right, so this would be u1 and u1, and this would be u2 and u2. If you wanted to do it that way, or you can just kind of keep it straight. It's not too hard to keep it straight, but you just have to be careful. Like, which u am I talking about? Well, this u over here was part of this function, so it's this one, and this u over here is part of this function, so it's that one. Right, so then at the end you just want to keep that straight and then plug everything back in together. 2x plus 1 here, and then plus 2 sine of 2x minus 1. Okay, so here's the derivative when all is said and done. All right. Okay, so that is a good example. All right. Now, what happens if you've got functions like, here's an example where we're going to have to actually use the chain rule multiple times. So what if you have a function that looks like this? Y equals sine to the third power of 4x. So notice here that, I mean, this possibly a better way to write this that's more intuitive would be to write sine of 4x cubed. Okay, so you can kind of see that the general power rule works here, right? So if you think of the outside function as being u cubed, you got the general power rule. But then when you look at this inside piece, the derivative here is, well, this is also a composite function, so you have to use the chain rule a second time. Okay, so let's go through it. I'm gonna kind of go through it like with the old notation first, or sorry, with the new notation, or with the alternative notation, and then we'll go through it with the notation we've been using on the examples, because this is a case where having this other notation in mind can sort of simplify things. So y prime, now recognize that the most outer part of it is just the cube function, right? So I can easily differentiate that and write 3 times the sine of 4x squared, right? And then I need to differentiate what's inside of that, which would be sine of 4x. Okay, so this would be, I've applied the chain rule once. Okay, now what I have to do, now notice, calculate this derivative. So I basically just differentiated this outside piece, and I got to figure out what this inside piece is. So notice that this derivative is itself a composite is a derivative of a composite function. So we have to use the chain rule again, right? And so what we would say is, let's kind of retain all this stuff out front, and let's differentiate this piece. So the outside function here would be the sine of u, right, which we know is the derivative is cosine. And the inside piece here is the 4x, so the derivative of that is just 4. Right, so now we've applied the chain rule twice. Okay, and then you can just simplify this thing. Right, so if you the reason I kind of would do this would just be to help people see that if you can see the inside-outside relationship clearly, then you don't have to mess about with all of the y equals something u and then u equals, you don't have to mess about with explicitly writing out those functions, right? If you can just see the structure, you can just go for it. Let's actually, so this would be 12 sine squared of 4x times cos of 4x. Right, so that would be the ultimate answer. But let's go through this example using the alternative notation as well. So the notation we've been kind of using, which there's nothing wrong with. There's nothing at all wrong with it. I just wanted to illustrate that sometimes once you've picked up a certain amount of experience, it can be, you can just kind of go right through the function and quickly identify the derivatives. But let's think about the function y equals sine of 4x to the third power. Let's think about it using the notation that we're kind of used to at this point. So first pass, it's kind of a two pass here. We're going to say y is equal to u cubed, and u is equal to sine of 4x. Okay, so then dy dx will be equal to dy du times du dx. Okay, I'm being very explicit with what I'm writing out here. So then it's d du of u cubed, and then d dx of u, which is the sine of 4x here. All right. So then we can differentiate this part. That's okay. So we can write 3u squared times d dx of sine of 4x. Now, this part here, this is where, when you're looking at how to do this derivative, like how do I do this derivative? Well, then you recognize, oh, this is a chain rule again. So I'm going to have to apply the chain rule a second time. Now, at this point, it might be wise to just plug your u back in here, right, and just say, okay, this so far I've got 3 sine of 4x times d dx of sine of 4x. So I still have to differentiate this part here. And so then you could come and you could say, all right, then my y now is sine of u, and my u is 4x. Okay, so I can just apply the derivative, or I can apply the chain rule again here. And so I would get, so this is kind of a note. So then I would say, all this stuff out front's already done, so I don't have to worry about it, just have to kind of hang on to it. Okay, like so. And then the derivative here would be, well, it would be du of sine of u times dx of 4x. Right, that's the chain rule applied again, right here. Just make it clear what I'm talking about here. So this is all of this. Okay. And these are both easy to do. So you get 3 times the sine of 4x. Again, just bringing that along. And then inside here, the sine of u, the derivative of that is cosine of u. And the derivative of 4x is 4. And so, yep, so then basically you've got the 12 sine of 4x times cosine of, and then what did we say the u was here? U is 4x. Okay, so that's that. So very good. Very good. I think this is supposed to be squared, though. Where did I drop it? Yes, right here. So 3u squared, so this is supposed to be squared there, squared there, squared there. Okay. Right, but notice that we do get the same answer. That's supposed to be a 4x as well down here. 4x. So notice that this answer and this one up above, they do match. Just have to be a little bit careful. Okay. Very good. So sometimes it depends on your level of experience. It also depends on, what the function is, but sometimes one notation is preferable to another. All right, let's see here. How about let's try another one kind of similar to that, just to see if we can do this. One more example here. So f of x equals cosine to the 4th power, and the argument is 2x minus 1. What's f prime? Find f prime. Okay. All right, so notice here a better way to write this might be cosine of 2x minus 1 all raised to the 4th power. If you write it like this, it's very obvious that this is a general power rule and then a chain rule inside of that. So the y prime, I'm just going to use the kind of newer notation. I'm going to try to switch over to that and see if people can, just give people some experience with that as well. So this would be 4 times cos of 2x minus 1 to the 3rd power, and then we got to differentiate the inside, times ddx of cos 2x minus 1. Okay, now can we differentiate this piece? Sure. So it's 4 times cos of 2x minus 1, just again bringing this along for the ride. Now the derivative here, right, the derivative of cosine is negative sine, so this is going to be negative sine, and then 2x minus 1, and then we have to differentiate the inside piece here, which is just a 2, so don't forget the 2. So this is very similar to the one we just did, just different function, different trig functions, different polynomials, but ultimately kind of the same structure. So you've got a negative, a 2, and a 4, so altogether out front you've got a negative 8, and then you've got cos cubed of 2x minus 1 times sine of 2x minus 1. Okay. So there's that derivative. All right, very good, very good. I think I will split this video into 2 parts, and so this will be the end of the first part. Okay.